discusses the use of stochastic hybrid modeling for the evaluation of the optimal preventive maintenance. As shown in the slide, the presentation is organized as follows. Let's start with the problem statement. So the mechanical design of a system is carried out after the evaluation of many factors like dynamic and thermal stresses, for example. So the knowledge of these all of this is often consolidated also from physical and mathematical viewpoint, and therefore this knowledge can be used also to evaluate the operating status and the remain useful life of a device. Furthermore, Industry 4.0 has brought a technological revolution in the industry, and cyber-physically nowadays systems are becoming a must. So there are a bit of data about the system operating, the artificial intelligence, for example, and the monitor condition technology have increased hardly. This gives the opportunity to run physical and mathematical model along with real time data coming from field to improve the accuracy about system status during the operation and remain useful life of a system. In general, the workload of the machine can be dynamic and depends on many factors. It is the actual manufacturing process that defines the operational condition of a job. Also, the aging is an important parameter because due to the aging, a machine can perform better or worse. The stochastic hybrid model adopts a Monte Carlo simulation and to sample the working condition of a system. The generic ITH job is simulated by sampling cumulative probability density function of angular speed, temperature, and loads. The nature of failures obviously is linked to the aging of machine to bearings. Consequently, the maintenance strategy is preventive and characterized by a preventive maintenance that we call TP by unit cost of preventive and corrective maintenance. The accuracy of a hybrid stochastic model depends on the accuracy and on the detail level used to describe the physical stochastic behavior of a system process. The most recent application it's possible to get information about the system operation in order to, let's say, improve the evaluation of the system aging and remain useful life. As shown in the slide, for the case for the use case discussed in this paper, loads, angular speed, and temperatures can be included in the model as they are known from the real-time operation. This is the model SKF for bearing system with fixed condition. So using this equation that we can see in the slide, we can calculate the expected time to failure, assuming accumulate probability of 10%. But this methodology, we know that is static. So using hybrid stochastic modeling, we want to add, let's say, more flexibility to the model in order to consider all the operating dynamics condition. Indeed, from the experimental data show that alpha depends on lubrication conditions, so depends on the operating condition as well that are dynamics. So we need to consider a corrective factor that we call alpha SKF, because this considers, as I said, the operational condition. Then we can see here a 6-degree polynomial that has been implemented and then it considers just the temperature, because we do that because we want to write the viscosity in terms as a function of temperature. Therefore, according to the operating temperature, the viscosity is calculated precisely, and consequently the modification of the expected life of the device. Then we applied the model to a case study of a preventive maintenance of a centrifugal pump, and once we define how the dynamic failure rate is calculated, the goal is to calculate the optimal preventive maintenance period, as we can see in the formula in the slide. Then, so we use a Monte Carlo process to simulate two different scenarios. In the first scenario, we simulate the behavior of a breeding system and its outcome by applying a preventive maintenance strategy at constant age, where the operative temperature T is fixed. Whereas in the second scenario, the operative temperature varies according to the formula that we can see in the slide. As a result, we can say that the specific maintain and cost and availability system have no effect on the maintenance scenario until the preventive maintenance interval is sufficiently short. Also, a good point is to say that under the operating parameter of scenario SB, it is necessary to reduce the preventive maintenance period in order to achieve the best balance of maintenance expense. And also, we have taken into account the system stochastic IV behavior allows for a more true availability estimate. Then, conclusion, an interesting management implication emerged that we can see in the slide. When the preventive maintenance duration is short, the specific maintenance cost and system variability have a little effect on the maintenance scenario. And at the end, we can say that we know that preventive maintenance never completely eliminates the failure. Therefore, a correct balance is made between preventive and corrective, and this implies finding the economic period of intervention that gives us the lowest operation cost. Thank you for having me. That's it.